Okay, this is chapter 3 course revision. This is gonna be a good 1 hour and a half at least. I'll turn on my camera for the right hand rule questions. Uh, anyway, let's start. So, question one. Oh, that ain't question one. Question one, define magnetism. Obviously, magnetism, it's a name. Okay, so magnetism is the observations given to matter that exhibits interactions similar to those between magnets. What are ferromagnetic materials? Or they are those that have strong magnetic forces, right? They're strongly attracted by magnets. In what way can permanent magnets lose their magnetism? These you have to memorize, okay? Mechanical shock, strong heating, and by influence of other stronger magnets, okay? So remember them: mechanical shock, heating, and influence by other stronger magnets. Describe magnetic materials. These are those, okay, ferromagnetic materials. Okay, when you say magnetic materials, think that means we're talking about ferromagnetic. They're those that can exhibit magnetic properties, okay? Are materials that are strongly attracted by magnets. These include cobalt, nickel, and steel. Memorize these, okay? Cobalt, nickel, steel, and certain materials called ceramics made by pressurizing powders to form solid bodies. So, ceramics are also ferromagnetic materials. Okay, so ferromagnetic materials, they are those that can be strongly attracted by magnets. They have strong magnetic properties. Always ferromagnetic, they're strong magnets. Okay, they include cobalt, nickel, steel. Okay, and steel is okay. You are supplied with two identical rods, and one of them is a magnet, and the other is just a steel rod. It's just a way to determine which is what in one and only simple move. So here's the thing: magnets, we're gonna call the magnetic force MF, and the electric force EF. So here's the thing: they both are the same thing. Like poles repel, opposite poles attract, right? So they're kind of similar for the most part. Except here's the thing: what's the difference between electric and magnetic? In a magnet, you have a north and a south pole, okay? And exactly in between them, we have something called a neutral point. And this is extremely important. The neutral point is where no charge happens, okay? However, the electric force, if you have a bar, we're talking about rods, the positive and negative charges are scattered all across the rod, regardless of where it is. So, if you bring one rod, and this is how they said in the course division, we're talking about the neutral point in the middle. If you bring the pole of one rod, you take the pole and you place it in the middle of the other pole, and you see that there's an attraction, that means the pole you just took is what? This is the magnetic, and the pole you're touching it to is what? The electric. But let's see, if you did it the other way around, if you took this electric rod and you put it halfway onto the neutral point, onto the other rod, and you saw there's going to be no force. Why? Because if you put the electric rod that has a charge onto the magnet, in the middle, we're talking about the middle. If you put it on the middle, there's going to be no force because it has a neutral point. Okay, so basically, if you take the pole and you see a charge, so let me just stop the yap. I'm going to show you the solution. Okay, approach the end of one rod to the middle of the other rod. If they attract, then this pole is magnetic. Okay, if they don't, then the end you just brought, the pole you just got, is non-magnetic. It's in this case steel. Steel is iron, by the way. What are the two poles of a magnet? How can one identify them? North and south. How can you identify them? Freely suspend a magnet, and the extremity pointing north is the north pole, and the other would be. Oh, okay, yeah, makes sense. Can we isolate a single magnetic pole by breaking a bar magnet in half? No, you can't. Because if you have a bar magnet north-south and you break it into two pieces, you're going to have north-south, north-south. Okay? So, as many times as you break it, no, breaking a bar magnet results in two other magnets, and isolating a pole is never possible. You never have a monopole. You never have north. You never have this. Okay? How do magnets interact with each other? Like poles repel, unlike poles attract. Construct a table that shows the difference between soft and hard magnetic material. We're going to memorize this like it's our name. Difficult to magnetize, always hard. Soft iron, soft. Used in permanent magnets and compass needles. Keyword here is permanent, hard. Hard steel is an example, obviously hard. Easy to magnetize, easy to magnetize is the keyword here, soft. What is magnetic induction and what are the two types of magnetic material? Anytime you see induction, whether it's electrical or magnetic, think of attraction. Okay, so magnetic induction is when a magnet attracts an object made of ferromagnetic material. خلاص يا أخي, when a magnet attracts an object, usually it's made of ferromagnetic. Remember, when what you're attracting 99% of the time, if something's being attracted, that means it's ferromagnetic. That's the classification. And then, okay, like let's see, let me see if I can kind of make it. So magnets, yeah, they either they attract the object or repel, or no, let's actually, I'm gonna split it into interacts and does not interact. If it interacts, that means it's ferromagnetic. Okay? If it's ferromagnetic, it can be split into hard or soft. If it does not interact with us, it's not ferromagnetic. Okay? If it interacts, that means your material you're attracting is ferromagnetic, which is either hard or soft. Remember, when you yani basically how induction happens is basically you're influencing it. So let's say you have a north and south, right? You have a north and south. You bring, I don't know, let's say an iron pole. The iron pole is ferromagnetic. So what's gonna happen? It's gonna be attracted. But you think, خلاص بس هيك it's gonna be attracted. Subhanallah, خلاص everything continues. No. When this iron is being attracted, it carries an induced south pole over here and an induced north pole over here. So it behaves like a magnet. Okay? That's how induction happens. It doesn't just happen, subhanAllah, they interact. No. The object being interacted behaves like a magnet. Okay? So ferromagnetic materials behave like magnets when put into contact with other magnets. Okay, a magnetic field B exerts a force of magnitude 3 north on a given magnetic pole P. Another field B prime simultaneously exerts a force magnitude of 4 newtons on P in the eastern direction. Find the direction of the resultant magnetic field P. If what the fuck am I saying? Find the direction of the resultant magnetic field if P is the north pole and if it's a south pole. Okay, so basically, if it's going north, yani, here's how I do it. Okay, and I put it like this, 3 newtons, and then I put it east, 4 newtons, right? Okay, so this is find the direction of the resultant magnetic field. Okay, here's how you do it. They're vectors, okay? This is in the book. The magnetic fields follow the law of superposition of forces. Basically, you can add them up. So if you have to the right and up, how do you make this as a force, guys? You have a resultant here, which is 5 newtons, because radical 3 squared plus 4 squared is 5. And then you need that. When we say direction of a force, it's always theta, okay? How do you find theta? Shift tan y over x, so 3 over 4, which is, I think, 37 degrees. 3 over 4 is 37 degrees, right? Yes, okay. And here they drew it, so east and north. Okay. But they just said, they put it as a bearing. East, 37 degrees north. Okay, yeah. So I guess when we're talking about directions, we're talking about bearings. How do you represent this? It's east, north, right? So it'll be east, 37 degrees north. Very easy. Okay. Or not, is this a bearing? This is the mariner's compass, no? Anyway, same, mariner's compass bearing. But you can say direction, or you can just say 37 degrees with the positive x-axis. And then you say counterclockwise. You can say this, I guess. But this would make more sense. Okay. For part B, if P was a south pole, basically what happens when you change the compass to a south pole, everything, just don't solve again, man. It just comes opposite. So basically, هيدي 3 to north صارت 3 south. Okay? وهيدي هون 4 east صارت 4 west. If you want to draw it, it's gonna be like this, right? 3 south on 4 newtons to the west, right? Okay. How can you find it? Again, it's gonna be 5 newtons. هون هيكون عندك 37 degrees. So how do you write it? West, 37 degrees south. If you don't want to waste your time, you just take the answer you got from part A, which is east 37 degrees south, and it was 5 newtons. It's the same magnitude. Obviously, direction doesn't affect magnitude, but this instead of north, heading north, east 37 degrees north, instead of going like this, we're going now like this. So west 37 degrees south. Okay, you can just swap it. Define a magnetic field and identify its direction. Magnetic field is the region of which I'm just gonna give you the answer. A magnetic field is the space around the pole of a magnet that exerts a force. So it's the space around the pole of a magnet that exerts a force on any magnet placed in that region of space. Right? It's the region that where you have a force on a magnet. Direction of a magnetic field is the direction of the force it produces on a north pole. This is a question that always comes. The direction of a magnetic field at any point. The direction is the direction of the force it produces on a north pole placed at that. Question 11. The south pole of a plotting compass points east at a certain point. What is the direction of the magnetic field at that point? Basically, look, we said the direction of the magnetic field. We literally just said it. It's the direction of the force on the north pole, right? Okay. Hone, think about it. You have a compass, okay? You guys know compass هيك, right? طب okay, إذا south راحت لهون يعني هون الإيست, right? يعني هون النورث. So where's the north? Where's the direction of the north pole? West. Okay, west. Describe and draw the magnetic fields of a bar magnet. The bar magnet is like this. It's always going from north to south. Okay? So it should just be. Oh, كمان they come and they flow in like this. Oh, one that goes straight in. Oh, they go out of south. Okay, and you need to show arrows, of course, and I prefer writing more than one. Probably three if you have space. So one last one. Okay, let's compare this with the answer here. Sorry. My bad. Okay, these on the side are normal, but it's the direction on the sides. I always get mixed up with this. Okay, I should remember it's always going into south, right? It's always going into south. So always going into south. So it should look like this, right? So if it's going in from here, so obviously in this case it's going out. Okay, memorize. Always goes out of north into south. Okay, that's a good way to memorize, I guess. Always going into south. So goes in, always going out of north. If you just memorize the general structure as like lines going like this, putting the arrows is easy. But the only hard part is remembering how the structure looks. You know what I mean? Okay, draw the magnetic flux pattern of a U-shaped magnet. I guess it's something very similar, right? Yeah, okay. So the U-shaped is gonna look, excuse my drawing, something like this. I'm not an artist, guys. North and south, okay? U-shape, it doesn't go back here. No, it doesn't. Like it doesn't go like from here. No, because this is inside the magnet, so you can't. Okay, so you're gonna have a lot of these, a lot of like squiggly lines. Okay, and obviously they're going like this, and then in the middle here, there's a space, and it's gonna be parallel in this case. Okay, so if you want to draw from the edges to the edge, you can't continue straight. This is wrong. You have to kind of curve it. So for this reason, and I always avoid curving my flux patterns, I always stick as close to the baseline as I can, just so I can just remain parallel. That way, ما بعذب حالي. I don't wanna make myself tired to think, oh, do I curve it, do I not? Okay, you only curve if you're out. You see, as you go further, by the way, look how much. Like here, it was parallel. You're going out more, it's curved. Now it's curving more as you go out and out and out and out and out, and you curve more and more and more and more and more. Okay, draw the magnetic field lines pattern between the unlike poles of two magnets facing each other. So here, it's two different magnets, okay? So don't make the mistake of drawing it like this, okay? Don't, please. It's two different magnets. So you have the south over here, you have the north over here, okay? It's gonna go like this. It's very like easy, okay? It can't go through the center. Yeah, it can. Why not? Okay, okay, like this. Okay, also you can't forget about the north that's on this side of the this side of the magnet. So it's also gonna have ones going in like this. We also can't forget about the south on this side of the magnet. So you're also gonna have stuff going out like this. Okay, guys, please fix your drawing in the exam. Well, my drawings shit so bad. It's very bad. So I think you get what I'm trying to draw. Uh, anyway, explain the following statement: field lines never intersect. I'm not gonna bother. I'm just gonna give you the answer honestly. At any point, we can only have one resultant magnetic field. If field lines intersect at a point, then that field will have two different directions. A plotting compass will point in two directions at the same time, which is impossible. Yeah, okay, yap it up, bro. Uh, okay, basically, uh, if what they're trying to say is, okay, if field lines intersect, then you're gonna have two fields. Okay, and that means a compass will point in two directions at the same time. Because it's one needle, how's it gonna point in two directions at the same time? So impossible. Okay, describe a method used to map magnetic fields. I'm actually drained. I'm not, bro. Right, read this yourself. Pause the video and read it if you want. So I don't think it's gonna come. Okay. 17. The diagram below shows a small compass needle placed on a bench under the influence of Earth's magnetic field. A bar magnet is now placed close to the compass in the position shown by the dotted line. Draw a new diagram to show the new direction of the compass needle. Okay, I guess it should just be downwards because it's gonna always point in the direction of the north, right? Okay, so basically, um, it doesn't face in the north. Well, it does face towards the north, right? But if you have a magnet placed beside it, the magnetic field, obviously, of this magnet is going to be stronger than the magnetic field of the Earth, right? Because the magnet stick, it's right beside this, the compass. So of course, remember the compass always points in the direction of the north pole, direction of the force produced on the north pole. Here, what's the force produced? Where's the force going? It's towards like this. So if you ever get a question like this, draw the magnetic field, okay? And you always goes out of the north, so it's gonna go down like this, right? And over here it always goes into the south, right? Okay, طيب. So at four different directions, if you have it over here, where's the magnetic field pointing? It's going up, so we're gonna continue like this. Here, where's it pointing? Going up. Here, where's the magnetic field pointing? Going down, so we're gonna go down. Here, where is it going? It's pointing down, so we're gonna go down. Okay, so that's how all these answers came. Explain how radial fields are used in the construction of current meters. So here I'm going to show you the answer. I'm going to try and explain it. But the most important part that you should know is for current meters, what do they use? No, it's a radial magnetic field. But what is it? You need to know for a current meter, أول شيء, how do you do it? You add two round iron armatures. It's like this. Remember, it's like this. If you open my notes, you can see it. Uh, okay, these armatures. Okay, again, excuse هيدا my my drawings. So basically, you have this north and south, and inserting a cylinder of soft iron into the gap. So over here, if you put iron, this is how it looks, huh? The armatures creates a radial magnetic field, and okay. So basically, here this creates a magnet field. Okay, and this magnetic field, it basically pushes any current carrying wire. It just pushes it, and it makes, obviously, when you push current and you exert magnetic field on it. So if you push a wire and you exert magnetic field on a wire, then the current is also gonna be like moving and straggling, whatever. What you need to know is this, okay? Current meter, you add two round iron armatures. Okay, that's the first thing. Okay, a soft iron. You need to know this. How does it look? Okay. Uh, my drawings are so bad, it's crazy, wallah. Okay, and then you put soft iron in the middle. You should know this. That's the first thing. You should know that it creates um, a plane symmetric radial field. Okay, and just no, this is the yap. Okay, parallel to the central axis, whatever. So for current meter, it's plane symmetric field that's created by two soft iron armatures. Now, hala, they tell you loudspeakers. Okay, loudspeaker is made of two rings, right? A circular magnet that looks like a hollow cylinder is used. So I'm pretty sure you have a ring, okay, outside the ring, and then you have the inside. So the magnet is fitted over bullshit the cylindrical tip of the bolt, which acts as a south pole. The second armature is shaped like a hollow cylinder of the same dimensions as the parent magnet. It acts as the north pole. Combination creates an antisymmetric field. So able to pull it into it or push out the coil carrying current. As the current varies rapidly, the coil moves in and out of the field vibration. Okay, so basically, the outside is the north, the inside is the south. Okay, think of it not as a ring, it's a ring with a circle inside of it. Okay, you get what I mean? So this is the ring over here. Try and make it a bit bigger. Then on the inside, you have a circular, like another one. This would be the south, and the outside one would be the north. Okay, this causes loudspeaker. You should know. It's made out of. It's a circular magnet. Okay, it causes an axially symmetric radial field. Okay, and basically what happens, the north and south, they start pushing, and it causes vibrations. Okay, to give it sound. Okay, so these question 18 and 19, I really don't like them. So I'm sure he's probably gonna get one question out of it, knowing the region. Yani. How can a magnet be demagnetized? Okay, we said mechanical shock, heating, and induction of a different magnet. But now I think they added a fourth one. It's storing it without a keeper. Okay, when you store a magnet, if you don't store it with a keeper, soft iron keeper, it's gonna be demagnetized. Okay, so we said heating, mechanical shocking and dropping, and causing an alternating current. An electromagnet can be used to demagnetize magnets. This is by influence of another magnet, right? Uh, Describe a simple method to prove that the magnetic field around a wire through which an electric current passes changes when the current is increased, the direction of the current is reversed. So you should know that the magnetic field is directly okay, it's in 23, we'll get to it. But you should know that it's directly proportional to the amount of current and the number of loops and whatever. Okay, so you should know if you increase current, that means the magnetic field. I'm just going to refer to it as B, okay, because in the formulas it's B. Okay, the magnetic field will always the magnitude will increase. Okay, how can you test? There are two things that can test the magnitude. That can test magnetic fields. You can test the direction where it's going by using a compass, and you may also test the magnitude by seeing how many iron, how much iron or how much attraction is going on. And the easiest thing we use is we sprinkle iron. So what we do is we put the wire, right? This is the wire, whatever. Okay, and it has current in it, right? And under it we're going to sprinkle some iron. And if you see the iron being concentrated and dark and whatever, that means the magnitude of the magnetic field is increasing and it's becoming stronger and there's more attraction. But if you see they're spread out, then akid the magnitude of the magnetic field is weak and it's little, it's not strong. Okay, how about the direction of the current being reversed? Now, when we're talking about direction of the current being reversed, that means we're talking about direction of the magnetic field, and only one thing can show me where the direction of the magnetic field is, well, that's actually a compass. So you're going to use a compass, and what results would you get? Obviously, the compass would be reversed. So here we would say, support a wire through a stiff card and sprinkle some iron. And then what happens if you increase the current? There's going to be more magnetic field. So watch the iron fillings concentration increase along the concentric circles around the wire. And then if we reverse the direction of the current, when the direction of the current is reversed, a plotting compass will point in the opposite direction. Draw a diagram to show the magnetic field around a straight wire carrying a current into the plane of the paper. State the rule you use to determine. Okay, so here's what we draw it. If it's going in, we draw it with an X. Okay, we're going to use, I always like to use 4 points. The direction of the magnetic field at 4 points. So what are we going to use? We're obviously going to use the right hand rule, right? Okay, so my camera's on for this part just so I can show you the right hand rule for this part. Always when you're looking at current, let me see, am I in the frame? Okay, yeah. Okay, so for 23, this one always comes. Oh, I think many people got it wrong last CA. What are the factors that affect the magnitude of the magnetic field? Okay, it's always the amount of current flowing in the wire and how far it is, the distance from the wire. Okay, so if you're talking about the magnetic field over here, مثلا, I'm just using, let's say this is the wire. Over here, it's going to be weaker than over here. Right here is going to be stronger than over here because it's closer to the wire. Okay, and also the number of loops that the wire makes, I think it should be somewhere. Okay. Uh, the diagram below represents a current carrying solenoid, and the arrows on the diagram show the direction of the current. Determine the polarity of the solenoid. Okay. For this one, again, my camera's on, but this time I think I inverted it. I just want to see if for this is going clockwise for me. So yeah, for the viewer, it should also be going clockwise. For this one over here, uh, it's a solenoid. For the solenoid, you use this right-hand solenoid rule. So in this case, you have it's either coming onto you or going in. Okay, you take your fingers, you curl them in the direction of the solenoid. The solenoid is coming like this. Then you extend your thumb. That means your thumb always points in the direction of the north. Okay, I just want to make sure. Right. Okay, so you go. Okay. Oh, because I press Alt Tab. Oh shit. Okay, wait. So when I was switching tabs, I'm not sure. No, then my recording's probably gonna look shit. Wait. Okay, so my recording kind of broke because I kind of paused the recording while recording without knowing that I was recording, so I had to re-record. So I reached 22 and I was using the right hand rule. Basically it was the current X, right? So you're gonna take your finger, you're gonna put it in. You're gonna put it into like because it's going inwards, so you're gonna point it inwards and you're gonna rotate your fingers and it's obviously gonna go clockwise. I think for you it should also be looking clockwise because I inverted my camera. It should be going okay, yeah, that's clockwise. Okay, so that means over here it's gonna be going like this, like this, like this, like this. Okay, and the answer they put it like this. Okay, and they said what you rule, obviously the right hand rule, and then 23. What are the factors that affect the magnitude of the magnetic field? The factors that affect the magnetic field are the current, always the current, and how far you are from the magnet, so the distance from the wire. Okay, so 23, obviously how much current you have and how far you are from the wire. If you're up here, if the wire is here and you're up here, it's obviously going to be weaker than when you're over here, down here, close to the wire. Okay, I just want to see how far can I go. Okay, here, because I just want to see how far my camera is. Okay, here. Okay, it's kind of like with the tip. Okay, uh, 20. Okay, what am I doing? 24, because I kept my camera on, because I think you need the right hand rule also here. For the solenoid, they gave you the solenoid here, and they're asking you, they said the arrows are the current, determine the polarity of the solenoid. So which one's north, which one's south? You take your fingers, it's coming on you, coming onto you, coming out onto you. Okay, so you take your fingers and you coil them like this. You extend your thumb, and your thumb is pointing to the right. Okay, let me see if it's pointing to the right also for you. Yeah, okay. So that means the North Pole is on the right, okay? So over here is the north and over here is the south. The polarity is like this. Draw a diagram to show the magnetic flux pattern. You just simply draw the magnetic field, okay? Whatever, like this. You can't forget these, okay? You can't forget them, okay? It goes in like this. The straight line, the horizontal one, and like this, okay? Let me see if there's any more. Okay, 25 also needs the camera. A current flows through a solenoid as shown below. What's the direction of the magnetic field created by the solenoid? To know the direction of the magnetic field, these are, by the way, I haven't seen a solenoid where it's not like where it like it actually goes uh like how can I explain it? You know, I haven't seen one that goes like this. Yeah. So until now, they're all been the same thing. So same thing. To know the magnetic field, you should always know the polarity. To know the polarity, you apply the solenoid rule. You take your fingers, you curl them outwards because the wire is going outwards, and you extend your finger, goes to the right. So on the right you have the north, and here's the south. So what's the direction of the magnetic field? You should draw it like this. So from B to A. Okay, I think that should be the answer, Yani. What's this? Going right hand, okay, this is for 24. Okay, yeah, whatever. Based on the right hand, the magnetic field is directed to the right. Okay, so here's the thing. The direction of the magnetic field, this is where uh, we always mistake the direction of the magnetic field. We mistake it with what we call the flux. Okay, the flux pattern is this one. Whatever. This is flux pattern, okay? But when you see direction of magnetic field, if you go back to grid question 10, we said the direction of a magnetic field is direction of the force on the north pole. Okay, so direction of magnetic field is the direction on the north pole. So if you go to question, نحن where are we? 25, right? Okay, here. We determined this to be the north and this to be the south. And on the north pole, where does it go? It goes to the right. Why? Because we remember we go out, right? If you draw the magnetic field, what's the direction of the forces? Like this, right? Okay, so where does it go? It goes rightwards. Does it go leftwards? Does it go through the solenoid? No, right? It goes outwards. Okay, so to the right. Always the direction of the magnetic field. You see, direction of the magnetic field is the direction of the force on the north pole of the object. Okay, if a current passes, okay, I think I think uh, yeah, I don't think there's anything else left for the camera, so I'm gonna pause and turn off the camera. Okay, 26. If a current passes through a solenoid and an iron core is approached coaxially, what? Okay, coaxially towards the solenoid, the iron core will be attracted to the solenoid. Explain using the principles of magnetic induction. So basically, the solenoid, by the way, when you turn it on, it when you turn it on, it acts as an electromagnet. An electromagnet exhibits magnetic properties and hence attracts the iron core, okay, which is made of ferromagnetic material. So 26, let me see how they say it. When a current passes through the solenoid, it induces a magnetic field. So the solenoid will act like a magnet and magnetizes the iron by what we call magnetic induction. Always when you're attracting, you're saying magnetic induction, okay? 27. Without changing the dimensions of a solenoid, how can you double the magnitude of the magnetic field as its center? You could say double the current, right? Double the current. Without changing the current or the dimensions of the former, how would you wind or rewind it to double the magnetic field at its center? You double the loops. Basically, you should know that B is directly proportional to the current and the loops. Okay, it's proportional to these two. وكمان you should know that it's proportional to the distance from the wire. Okay, please know these. So if this increases, this increases. If this increases, this increases. If this increases, this increases. No, 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 no. Inversely proportional. Shit. Inversely proportional. So directly proportional to 1 over. This means inverse. So basically, obviously, if why am I saying inversely proportional? Because if the distance from the wire increases, is the magnetic field going to increase? No, no, no. It's going to decrease, right? So it's directly proportional to the current in the loops, but inversely proportional to the distance from the wire. List the properties of electromagnets. This game, I remember. The magnetic field can be switched on and off. Electromagnets can be shaped like bars, horseshoes, or other shapes, and it can create much stronger fields than permanent magnets. Okay, question 29. So we listed the properties of electromagnets. This came in the CA, and then also list some applications of electromagnets. This also came in the CA, and people didn't put tape recorder. They put erase head. Or wait, no. See, like here, tape recorder, right? This like the applications we know them. Everybody knows them. But here's the thing. Uh, which head, right? Uh, is it the erase head or is it the tape head? Okay, so apparently it's the erase head because the erase head houses a current carrying whatever. Um, so it's the erase head and the recording head. They both have electromagnets, but I think they gave us some bullshit like I don't know, some playhead. The playhead, yeah, I remember the playhead. We don't care about the playhead. We only care about the erase head and the recording head. Okay. So if recorders, electric valves, relay switch, this one's easy. Okay, design an experiment to demonstrate that the magnitude and the direction of electromagnetic force depends on the relative direction of the magnetic field in the current. So I'm just gonna give you the solution. Basically, anything you want to test the direction of magnetic field, current, and force, the electromagnetic force. Remember, anytime you see electromagnetic force, you're talking about IEF. Okay, and just memorize this experiment. It was in the book. Okay, it looks like this. Basically, they got a wire. Okay, there are three things that factor into the force: IBF, the current I, and the direction of the magnetic field. So basically, your current is moving to the right. Your north pole is it acts perpendicular. It has to be perpendicular. Okay, it acts perpendicular, so it goes like, I don't know. I B. It's upwards, so the force will be like this. Okay, so if you use the IBF rule, basically what I'm trying to say is that the force depends on the current and the magnetic field. And to test the current, you would change the poles of the battery, because you know it always goes from positive to negative. How would you change the magnetic field? Bro, just take the magnet, take it out, and flip it, and put it back in. What's gonna happen? You're now gonna have a south, so the force will be in a different direction. So basically, where your north pole is, the direction of your current, they play into the force. And how would you do that? You design a circuit in the swing, place it between the poles of a U-shaped magnet. Okay, allow current to pass, and it has to be perpendicular. Huh? Allow current to pass and observe how the wire moves. Change the direction of the current, because there's going to be force. Obviously, the wire is going to move if there's a force. Change the direction of the current by exchanging the connection of the terminals of the battery. So make it positive here, negative here, and then see how the wire moves. And then change the direction of the magnetic field by exchanging the poles of the magnet, and also the wire will move differently. Okay. 31. Design an experiment to demonstrate that the electromagnetic force depends on the magnitude of the magnetic field, the magnitude of the current. This experiment will be used to assess your ability to design an experiment, to investigate a problem, to select correct items, to assemble and use the apparatus correctly, formulate, generalize. Okay, that's too much talking. Okay, this is basically for people who are doing A-level physics or AS physics, the lab part. We're not required to know this, but I'm just gonna show you. Design a circuit, swing plate. This thing is the same thing, bro. Vary current using a rheostat. Anytime you want to vary, remember it depends on the current. If you remember earlier, we had something where it depended on the voltage, so we had to use, I remember the characteristic curves of the IV characteristic curves for the filament lamp and whatever, they depended on the voltage, right? So for that reason, we use the potentiometer. But in this case, since we're talking about modifying the strength of the current, you're going to use something called a rheostat. You guys know rheostat varies current, potentiometer varies potential difference. And also, we want to we want to test the magnetic field. We want to increase and decrease it. Use How do you do that? Just use a bigger or weaker magnet. Okay. Question 32. A wire AB is placed between the poles of a magnet. When the current is turned on, the wire AB will experience a force. The direction of the current is reversed. What effect will this have on the size of the force, direction of force? The size of the force doesn't change, right? It's the same force, because you're using the same magnitude of current, same magnitude of the magnetic field. But the only thing that's going to change, what? The direction of the force, right? It's going to change. It's going to be the opposite direction, right? The direction is reversed. Give two ways in which the size of the force on the wire AB could be increased. There are two ways. Remember, IBF, either increase current or increase magnetic field. Okay, to increase the force, increase current or increase magnetic field. State the rules used to determine the direction of the force exerted by magnetic field. Okay, this came in many people's prep list and they still get it wrong. Okay, this was the first blank. The right hand rule used to determine the direction of the force. How do you use the right hand rule for force? You always use your thumb for the current, so I. Use your index for the magnetic field, B. And your third finger, people put the middle finger, I don't know why, or ring finger. I don't, your third finger will show you the direction of the force. Okay, so this was the third blank, I remember. So, F. You guys remember IBF, the rule I gave you? Okay, always, whatever, you use IBF, okay, to determine the direction of the force. They must be perpendicular, okay, the current and the magnetic field. Okay, what else did he say? That's the first rule. The next rule is the motor force rule. If you curl your fingers of the right hand in the sense of the smallest rotation from the direction of the current to the magnetic field, the thumb points in the direction of the force. Again, it's similar to IBF, but I don't like it, but you should know it. You have to know it. Okay? The motor force rule. Okay? The right-handed screwdriver rule. If a right-handed screw is turned by a screwdriver so that the notch in the screw head rotates from I to B, the screw advances in the direction of F. That's actually S. Oh, okay, yeah, that's actually okay. Yeah, I like this rule. It makes sense, but saying I ain't using it. Okay, we're using the right hand rule. It's the best one, in my opinion. But you just need to know that these three all exist. State where am I? Okay, we did 30. When is the magnetic flux maximum? When is it zero? Remember, magnetic flux phi is equal to BA cosine theta. When is it maximum? It's maximum when theta is equal to 0 degrees. And when is it 0? When theta is equal to 90 degrees. Don't mix it up, huh? Uh, here. The flux is maximum when the field lines are perpendicular to the plane. When we say it's perpendicular, if you have here the field lines, if it's perpendicular, معناتها the plane is like this, it forms a right angle. And how much is the angle of the normal? It's 0 degrees. Remember, we always take for theta, it's the angle the normal makes with the field line. Well, they're along it, so that's why here, in this case, theta is equal to 0 degrees. So when it's perpendicular, theta is equal to 0 degrees. Okay? How about if you had the field lines like this, and you had our plane lying on it? Theta is going to be equal to 90 degrees, because the normal in this case would go up, and it would make a 90-degree angle with the field line. So, and it's 0 when the field lines are parallel to the plane. Okay? So when the field lines are parallel to the plane, it's 0, and when the field lines are perpendicular to the plane, it's maximum. Okay. 35. List the factors on which the magnetic field depend. Okay, we just said magnetic field, magnetic flux. It's BA cosine theta. So it depends on the magnetic field, the area of the loop, and the orientation with respect to the magnetic field. When we say orientation, we're talking about the angle it makes, the theta. Okay. Section 3.3. I think we have one more page. خلاص, we're done. Two current carrying wires are placed parallel to each other. Determine the nature of interaction between the wires if they carry parallel currents, anti-parallel currents. So I'm going to draw it for you. I'm going to draw a wire here and a wire here. You're going to have around it a magnetic field, right? And also over here, I should have made it a bit bigger, right? They're both moving up. So they will both have a magnetic field like this, right? Think of it as going around the wire, not like in, like imagine the wire is vertical and you have it around. Okay, and same thing over here. Okay. My fault, gang. Over here, flux patterns are not allowed to intersect. So basically I'm retarded. Um, over here, like this. Okay. Yeah, so they get close, so they're gonna attract each other. There's gonna be some sense of magnetic force pulling this and pulling this. So what's gonna happen? Since they're both in the same direction, they're both gonna be acting clockwise. Okay, but not necessarily clockwise, but you get the point. Okay, so they're gonna attract. Okay, they're both gonna attract each other. But let's say if you had one going like this and one going like this, so you'd have your magnetic field, right? عادي. But this one, let's say مثلا it's going clockwise. Okay, here it's going to be going anti-clockwise. So since it's opposing the direction, it's going to repel. So if they're in the same sense, they're going to attract. If they're anti-parallel, yani opposite directions, they're going to repel. Because last page, describe the working principle of a moving coil galvanometer. We did this before, no? It's an ammeter. Oh my days. Oh. Okay, when a coil is in, I'm gonna read this and summarize. Okay, so yeah, to wrap this up, simple terms. Basically, know this: if you have n turns, then the number of force will be the number of turns multiplied by the force. So this is just to prove that the turning effect on a current carrying coil is directly proportional to the number of turns. So if you turn 3 times, it's gonna triple. Turn 4 times, it's gonna quadruple. Okay, that's the first thing. A galvanometer, this one makes sense. Okay, a galvanometer will be more sensitive will be if it gives the same deflection for smaller currents. So let's say, and I have, I don't know, 6 milliamperes here. Okay, and I give a full deflection. Okay, and then I have another galvanometer, but at 4 milliamperes, it gives me a small deflection, as it gives me a full deflection. What does this mean? It means this one is more sensitive. Something sensitive, that means it responds to change more easy. Okay, so obviously, if it gives the same deflection for smaller currents, it's more sensitive. So this means that a more sensitive galvanometer for the same current would give a bigger deflection. Okay, so let's say like you have your galvanometer over here, and this is, I don't know, let's say 120 degrees. Okay, so its deflection is 120 degrees. Okay, for 4 milliampere. But if I came and got a more sensitive galvanometer for the same current, 4 milliampere, it's going to deflect maybe 150 degrees. Okay, over here like this. Okay, this would be the more sensitive one, just so you can kind of understand. Okay, one way of doing this is to use a spring with a smaller constant. Another way is to get more turning effect out of the current. One way of getting a bigger turning effect is to increase the number of turns in the coil, right? We can get more turning effect if you increase the number of turns in the coil. The other way is to use a stronger magnet. So basically here they're just discussing how can you get a higher deflection. Higher deflection means there's higher current. Higher current means there's more turns, okay? Or stronger magnet, obviously. Describe the working principle of the direct current electric motor. I low-key forgot this, so I'm gonna read it again and then summarize, okay? Okay, basically, for the direct current electric motor, so this is a lot of yap, okay? I'm gonna open the diagram. I watch the YouTube video, can't help me any. So basically, let me try drawing. So you have this north, okay, over here, and you have this south, okay? Basically, what they do, yeah, that's a bad drawing, okay? Basically, you have your magnetic field, right? Okay. Okay, but this is, you get my point. This is very, very, very inaccurate, but you get my point. So what they do is they're like, oh, now we want a motor. A motor spins, okay? So they come, they get a coil, and they wrap it like this, okay? And you guys know, you have a magnetic field. You have a coil, a wire. Turn it on, you're gonna have current. What happens when you have current and a magnetic field? There's a force. So what's gonna happen? It's gonna turn. But here's the thing. When it turns, okay, what when it turns, it's gonna turn until a point where now it's gonna have to turn backwards so that it maintains a magnetic field. So for that reason, when it turns up here to the 180-degree mark and makes a half rotation, what do? We swap the direction of the current. That way it's actually gonna continue its rotation. Okay? Because if it rotates up here, it's perpendicular, it's gonna have to rotate backwards. But to prevent that from happening, what we do is we swap the direction of the current. So if, let's say, مثلا, this was the positive side, and this was the negative side, it's actually not the other way around. It doesn't matter, but my point is, if this was the positive or negative, this is going to rotate until it reaches up here, and it's going to have to rotate back, okay? But for that reason, we swap it. So halfway through, this is going to become positive, this is going to become negative. Some people are going to ask, okay, how do you do that? Okay, so here's the thing. It's connected to what we call a split ring commutator, whatever. Okay, so it looks like this, and it has this small gap over here. So here's how it works. You have a battery over here. Let's draw it in green. You have a battery over here that has a brush over here and a brush over here. Okay, I'm gonna label this side as use black. This is the positive side. This is the negative side. Okay, you see it has two halves. These are connected to a battery with C. Okay, so what happens is this coil is going to rotate. So this positive side is going to go here. This negative side is going to go here, right? Let's say it's rotating counterclockwise for the matter. Okay? But we said once it establishes the half rotation, it's going to have to rotate back. To overcome that, that's why we have two plates, the positive and negative plate. So when it goes here, this positive is negative. If it continues to rotate just a bit more, what's gonna happen? This brush is now gonna become on the positive plate, and this brush is now gonna become on negative plate. So if you can imagine like a plate, okay, like this. This is the positive side, this is the negative side. Continue rotating it. You're gonna have the negative side here, the positive side here, right? Rotate it just a bit more. You're gonna have now the negative side over here and the positive side over here. Rotate it now just a bit more. I'm talking in the counterclockwise sense, huh? You're gonna have now the negative side here, positive side here. So you see how they're always alternating? Okay, this is the whole point of a split ring commutator. So we can switch the polarity. Because when you switch the polarity, it allows for a full rotation of the coil. That way, you can actually have rotation. For people who are interested in mechanics and engineering and whatever, this is the basic motor. Okay? In Arabic, بنقول له motor. Okay? It starts spinning, and basically, this is where the fundamentals of mechanics happens. So this is kind of how it looks. You have the brush. So the brush, you should know it's made out of carbon. And in case they mention it, well, actually not, I didn't even read it. So the DC electric motor is a device that can turn through many full revolutions under the action of the motor force. Okay, where a DC supply is basically battery, yani. Okay, such that the wires that lead to the coil can remain at rest and the torque is always in the same sense. Okay, what are the wires that lead to the coil? They're saying in no these wires. These wires, they never move. Okay, but the coil moves, but the wire should remain at rest, and the torque remains constant. What do I mean by torque remains constant? As you know, it never stops. It keeps on rotating. Okay, so the torque is always in the same sense. I don't want it to go change back to the right. Okay, so the wires remain at rest, and the torque any turning. Okay, some people don't know what torque moment. The torque, the turning effect is always in the same sense. This is the function of the split ring commutator. The working principle is what? You have a current carrying coil placed in a uniform magnetic field, right? We know it can make a half revolution under the electromagnetic force. طيب, what happens after that? You now reverse the current, okay, when the coil becomes perpendicular. When I say it becomes perpendicular, يعني خلاص the coil is like, it's in the book, wait. Kind of like, if you turn this a bit more to the left, this is going to be perpendicular. Okay, when it becomes perpendicular, we now reverse the direction of the current. That way it can continue turning. So you reverse the direction of the current in the coil, and the new electromagnetic, there's not going to be a new electromagnetic force that's going to continue pulling it down. Okay, we'll turn the coil another half rotation. The torque, whatever, will be in the same sense. So basically, a continuous rotation is going to continue in one direction. It's acquired how? Half revolution after half revolution, by reversing the sense of the current after every half revolution. So you should know this. After every half revolution, the current is reversed. He could ask that as a question. Where does the energy to rotate the shaft of the motor or to move the coil of a speaker come from? Obviously, from electric current, right? And then when you turn on the battery, energy comes from electric current. It's so easy. In what ways is the energy of the battery used? It uses, part of it goes as useful energy, and the other part is dissipated as heat due to resistance in the wires, right? You should know this. These are very easy questions. If they come in the exam, any very easy ones. What is the most favorable position of the coil relative to the magnet for the brushes to lose contact with the rings? Remember, the brush is here. For them to lose contact, oh, this is an inaccurate diagram, sorry. For them to lose contact, that means the brush is neither on the positive nor the negative side, okay? And for that to happen, I really drew it very badly. I'm sorry. Um, should it should be like this. Sorry, the positive. If you want, you can look up DC motor on YouTube, and there are many videos, animations that explain it. So it should be, this is the positive, and this is the negative. So when it rotates and the brushes are facing the space, not in contact with any of the rings, where's the coil? It's perpendicular. It's straight up, right? Not like this. It would be straight up. It would have turned. And when it's straight up, you could say it's perpendicular or it's facing the magnets, whatever you want. In the document, they said where the torque is zero. Torque is zero, by the way, is when it's facing upwards, because there's an instantaneous moment where it rests, where it stops moving, okay? When it's like straight. That's why the torque at that instant is zero. Okay, nearly zero. And also we can see where the coil is facing the magnet, because at that instant, it doesn't look like this. Please remember, it doesn't look like my diagram here at that instant. It would be like straight up, like, how can I explain? It would be straight up. You get what I mean? It would, and facing this, okay? So it would be facing the magnet. Okay, the top question. The diagram below shows a place between the poles of a magnet to create a DC motor. State the direction of the current in the loop. Obviously, current goes from positive to negative, so it's going to go from A to B to C to D, right? A, B, C, D. State the direction of the loop's rotation. You need your right hand rule for this. Let me يا أخي, look, the current is going in, okay? So you put your finger in and you rotate it, it's gonna rotate in the clockwise sense, okay? So that means the direction of the loop will be clockwise. Explain why the loop rotates in the magnetic field. Explain here. Why right hand rules when we curl the fingers from the direction of the current towards the direction of the magnetic field. The thumb points in the direction of the force exerted on charges moving in the magnetic field. And the magnetic field exerts an upward force on part. What? What? Okay, I explained this completely wrong. I'm sorry. For rotation, you can't have only one force. You need two forces because we call it a torque. To have a torque, you need to have something pushing it down and something pushing it up so that way it can rotate. Okay, so let me show you, open my camera so I show you what happens. So basically, you have, okay, we said the current is going A, B, C, D, right? So you could say the current is going in, okay? Depending, remember we have two sides, these two sides. Let's talk about, I don't know, let's say CD, okay? So basically, you have A, B, C, D, right? In AB, current is obviously going in. In CD, it's going out. Because remember, we're going A, B, C, D, okay? We're going to look at both sides. You have two sides. I just want to see how centered is my camera. You have two sides, okay? Let's talk about AB is here, CD is here. I'm going to start with CD. CD, it's coming out. Remember, we're talking about a force. You have a magnetic field, you have a current. We're talking about a force. It's coming out, right? You have to see the magnetic field. It's going from north, which is on the right, to south. So it's coming out, the current. That's I. B is going to the left. So extend your middle finger. Where's it going to go? Down. Okay? So that means CD will exert a force downwards. How about AB? AB, it's going inwards. Again, the magnetic field is going to the left. So I is inwards. B is to the left. Extend your middle finger. It's going to be going what? Up. Right? Up. So the force on AB is going to be going upwards. So you have a force down. I could say, مثلا, I don't know, you have my phone. You have a force that goes down, pulling it here. If I just put it down, it's going to go like this. But so I want it to turn. So I need to go down and up, right? So a force pulling it up and a force pulling it up. So together, the couple causes the rotation. Okay? Then he said, list two factors that determine the frequency of the loop's rotation. So basically, the strength is obviously the strength of the current and the strength of the magnetic field, right? The loop's rotation caused by the force. What changes the force? It's I and B, right? So the current in the loop and the magnetic field. Thank you so much for watching, and good luck in your final or whatever you're watching this for.